Hey folks, let's get started. So it's my pleasure today to welcome Professor Jenkins to give today's CNRE winter seminar talk in today's CNRE's winter seminar series. So Professor Sun is the Michael G. Parsons Collegiate Professor of Naval Architecture and Marine Engineering at the University of Michigan. She also holds appointments in EECS and mechanical engineering. And Professor Sun has been at Michigan since 2003. And she's unique in that prior to coming to Michigan, she was at the Ford Research Laboratory for 10 years. And she's an expert in controls. And at Ford, she worked on advanced powertrain controls. And Professor Sun holds 45 US patents, in addition to publishing over 300 journal and conference papers. And she is extremely distinguished. She is a fellow of the National Academy of Inventors, of IEEE, of the International Federation of Automatic Control, and SNAME. She is also the recipient of the 2003 IEEE Control System Technology Award. So, thank you again. Talk to us.
For the invitation, and thank you all for taking the time. As the title suggests, I'm going to talk about something specifically on control co-design. Try to explore the synergy between hydrodynamics and control. See, it's working. I think probably all heard about this siloed mentality in design and in product development. People design it through the wall and then get it manufactured and put it out to the market. So this is so-called over-the-wall engineering. When it comes to the control, that's pretty much the situation. So this is the so-called design and then control paradigm. First do the physical design, then hand this over to the control engineer to do the control design. So in most of the cases, control is built as an afterthought, and also control is cheap in many industry because you can just change some code to change behavior. So this has been the practice for a long time, and it's still the practice for most of the engineered system these days. Of course, sometimes it doesn't work. This process doesn't work. So what we do iterations. So you have design, and if the control engineers cannot make it work, or there is some new insight discovered during the control design process, we feed it back to the hardware design. And goes in this loop of iterations. Well, of course, the problem with that is it takes long cycle, and also you talk to different people, so it's not it's like it's still the wall, it's still the overwall practice, except that you threw it back through the wall, then go back and forth. So as you can imagine, there's limitations. There's some fundamental limitations. The performance will not be optimal. So we achieve suboptimal performance. And this is the picture from this recent book. I think that best illustrates in general what are the fundamental problem is. Suppose this is the value function that you're optimizing, and there is constraints, and those highlighted by red are the forbidden areas. So the best you can achieve is this blue point. But if you do this sequential design, that is, you design in one dimension, then in another dimension, you will not get to this point. And also where you end up with depends on where you start. For example, if you start from this A10, and you push in this X1 direction, you end up here. If you start with this B and you push in the vertical direction, then you iterate, end up here. Okay. It's not just that we don't get the best performance. Sometimes we also limit our candidate pools. For example, you will not consider unstable plans. They will not be in your candidate pool. But if you consider control at that time, you say, okay, I can stabilize it through control. And then you evaluate in your design. Then you can include this in your design pool, right? And many other operational constraints, such as controllability, stability, and also the sensor placement, etc., those will not be considered at early stage of physical design. So the control co-designs try to bring these two together, the physical design and the control design, and explore those two spaces simultaneously. So what I'm trying to do here today is first, we'll talk about the motivation and why it is not widespread practice. What are the challenges? Then I will do two examples, two case studies. One is on the planning hall design. And this is what I call the control-enabled optimization. Another is the hydrokinetic turbine design. So those are two examples that we explore the hydrodynamic and control interaction and show that for co-design, what we can achieve and what benefit it brings to the table. Then I will end up with some conclusion. So I like to first start with this example of planning hall design. So for those in the hydrodynamic research domain, you might be aware of this planning hall that's high speed, used both for recreational and the military applications. And to get it planning, then you design it so that this so-called trim angle will determine, which is going to be determined by, for example, where you place the center of gravity, how do you distribute the weight, and also how do you design the, for example, the dead rise, the whole ship. And from the efficiency point of view, the lift to drag ratio is an important performance criteria. And it is highly dependent on the trim angle. And so this gives the general function or the trend of the relation of the lift to drag ratio as a function of the trim angle. Of course, we want this ratio to be high. If we only limit ourselves to stable planning hall, instability in the planning hall, when it goes to high speed, you get into this porpoising. And you probably have seen or experienced that at high speed. And we don't want to get into that, of course, right? So we limit ourselves to the stable region. That's where your range of design, that's your design space. So the best we can achieve is this number here. But if we are allowed or able to explore the unstable region, then the best achievable performance will be somewhere here. So we have different of performance improvement. But that room is only available to us if we incorporate control at the early stage. Okay. So why do we want the control co-design? Well, this is the case when we have interactions between the hardware and the control. So if there's no coupling between those, then the sequential design performs quite well. The other point is we do have stringent performance requirements. If you don't care about performance, then the sequential design will also be okay. It's this two together that motivate us to explore those two phases simultaneously to get the best we can get. So I think that the most compelling example is this F-16 fighter jet. You probably have heard about it. This design is not possible if you don't bring control into the design, because its open loop is unstable. But you need that for maneuverability, for lightweight, for efficiency. So that's a positive and compelling example. Another example, actually, it's on the other side. I don't know if have you heard about HCCI, homogeneous charge compression engine, right? This engine was designed to have the advantage of both diesel and spark ignition. It has supposed to have the efficiency of the diesel because you can go to much high compression ratio, but have the low emission of spark ignition because of the low temperature. But why we don't have HCCI running on the streets these days? Well, part of the reason is it's fundamentally not controllable. It's hard to control. You can run this engine at steady state speed, but if you want to go from one operating condition to another operating condition, the transition is fundamentally very hard and require different, sensor and actuation. So those are the two examples that. So what do we expect by exploring this two design space simultaneously? Well, first of all, we expect to get what we call the optimal performance, because we're not going to be limited by the angle of what we attack the problem. So we can improve the design in all different aspects with the mindset of how it's working in operation, not just in the CFD, not just in the design space, right? But to me, I think that the most important thing is the process helps us to discover the physical interactions and gain insight that will help us to formulate the problem and address the constraints properly. Well, if it has this kind of advantage, why it's not done widely? Why we have not done it, for every design problem, right? Well, it's fundamentally hard. It's fundamentally a multidisciplinary design optimization problem, and involves multi-physics and also multi-fidelity models. And the dimension of the optimization is going to be very high because we're talking about the physical design variables and also control variable. The control variable is a temporal variable, which means at each time instant, we're making decisions, right? But I think to me, the most important thing is the mindset, the different mindset and different language we're talking about when we bring different people, people from different disciplines together. For example, that sequential design problem, it has the advantage of being modular, right? We do, you have a clear boundary and the domain expert feels comfortable within that boundary. So this is modular or integrated. And the second mindset difference is static versus dynamic optimization. Design people, most of the time, they deal with the steady state performance. But when it comes to control, we're mostly concerned with how we make transition, how we go from point A to point B, how we go from, when you do the high acceleration, how do we go from cruise to the high speed? So that involves feedback and dynamic models. And we also have interest in both spatial and temporal access. For controls, there's also open loop, closed loop. So all this makes the problem hard. As far as I'm aware, there's no general framework and tools that are available for control co-design in general that solve all the problems. But for specific problems, we have some successful experience. And also there are some general tools that can be adopted to solve those problems. But you need to work with, people from different disciplines, different domains to make that happen. So the CCD, the control co-design, is kind of quite active community these days, but it is pretty young field, I would say, compared to, for example, control or design. Initially, there are some, I would say, academic problems that were addressed in early 2000s and try to incorporate the notion of, for example, controllability in design. Can we pitch up the physical system to have good controllability? Then this open loop optimization or direct optimal control was introduced into the system. It was more sophisticated problem. More recently, this control co-design, especially by a group of community, is pushed or advocated as a design game changer. And there was, for those interested in hydrodynamics, I think those are probably the most relevant recent program. So there's 2 ARPA-E programs dedicated to control co-design. One on the offshore wind, another on the hydrokinetic turbine. And we have worked on this SHOCKS program, which just finished. So what I'm going to do is, as I said, I don't feel like there's a general or the magic tool to deal with control co-design problem. But there are interesting, problems and also relevant tools that can make the control co-design both, scientifically interesting and technology productive exercise. So I'm going to talk about two recent examples. The first is the planning hall design problem. And here we're interested, of course, in the efficiency. So we want to have optimal lift and drag ratio. And we understand that this is achievable if we consider unstable design, open loop unstable. But we also have to look after this sea keeping performance. The harsh motion is the primary cause for injury, especially for those military, and also the maneuverability. So initially, this planning hall is a sequential design problem, and they design the hall from hydrodynamic perspective. Then they bring in the control system, what they call the active control system, to mitigate this instability and also to improve the sea keeping performance. So this is work actually by one of my former PhD students who addressed this problem from control co-design perspective. This is fundamentally hard even for control people, even in the sequential design process in the second phase of the design, because it's highly nonlinear, and also there is very limited model available, and we know that the time domain response is highly sensitive to the design parameters. And also what kind of design we can achieve really depends on control configuration. When I say control configuration, it means what feedback, whether we do the feedback with the pitch, heave, or speed, or what is the sensor, and what we use to make a decision on the control system action. So for this problem, our solution is we have combined both the frequency domain and time domain and come up with a special parameterized model so that those design parameter of the dead rise or the center of gravity can be explicitly captured in the model. Then we also did the control analysis to determine what's the best feedback from just doing sensitivity analysis. What is the best feedback structure? Because for this, open loop optimal control will not be feasible because of the modeling issue and because of the computational issue. So we ended up with a linear quadratic regulator with two specific feedback input, which is a heave and a pitch. So now we parameterize the control with the gain from in the feedback loop. So I'm not going to go through the optimization process, but I just like to highlight the results. So we consider those performance metric and look at this average sea wave drag and also the sea keeping performance using this specific criteria. And the problem setup, as I mentioned, we explore this. One is the dead rise. Another is the longitudinal center of gravity, which is determined by the center of gravity or the weight distributions. And for the feedback in the control space, we consider the pitch velocity gain, and we fix the others. So we have just two parameters in the physical design space, one in the control design space. So here are the results, and this is typically what we call the Pareto front. We have one axis is the improvement of efficiency, another is improvement of seed keeping. And those two objectives are fundamentally competing to each other. So when you improve one, you sacrifice, you compromise the others. So here are 4 different scenarios. One is we have no control, we just do the hardware design. And then we second one is we do the hardware design and then we apply control. So this is sequential design. And with the control, we bring down the seed keeping performance and we improve the seed keeping performance. And this red is the co-design, but we impose the open loop stability constraint. It does get better performance than the sequential design, but the most significant improvement comes from the co-design without open loop stability constraints. But of course, the closed loop is stable because we have the feedback to stabilize it. So if we look closer into how this improves the performance, so here are the 2 different metrics. The open loop are this blue line, blue curves, and this is without active control system. As you can see, if we improve one, we have to compromise the other. So there's no synergy that between those 2. Okay. But if we do the open loop, I think there is, you can't see it, but here in this region, actually, it is going down like this. So there is a small window where we see, even within the stability constraints, we see that we have both of those metric improve. So this is when we have the synergistic condition, but we have to bring in the control to explore that. And if we consider, if we don't have stability constraints, and again, you cannot see it here, but trust me, this goes like this, come down and stay here, then take off. Okay. So within that region, again, we see both performance improve. So with the control, we got to explore these regions when we have a synergy. We improve performance in both axes. Have to, to improve the other. So here is the case study that, if we do sequential, we get one design and it has very good efficiency, but it's the seed keeping performance is really bad. Then we bring in the control to bring this down to this requirement level. So this is one design. And if we do the co-design, then we achieve the requirement, seed keeping requirement, by exploring the best performance. As you can see, those are 2 different designs in terms of the beam and the longitudinal center of gravity and dead rise. And of course, also the controls. And when you look at for different seed states, you can see the advantage of the co-design compared to the sequential design. And those are the 2 final designs. As you can see, they are different. The fuel tank, for example, the location is very different to achieve the efficiency. Okay. So with that, I want to move to the next example, which is a more recent example. This is for the marine hydrokinetic turbine for rivery and tidal current energy. We have a lot of those renewable energy. They are untapped. So here are some numbers. So if we can harvest most of those, then we can meet, we can provide the clean energy in a big way. Another important thing compared to the solar and the wind, this is more reliable because the water flows in those directions day and night, right? And the wind does not have to blow. And also they are typically co-located with the demanding center. So this is one of the ARPA-E program I just mentioned, and the control co-design is the main theme of that. The program is called SHARKS, and our project is called Reconfigurable Array of High Energy Ducted Turbine. So what is the CCD? By the way, those are the students and the research scientists. Kartik is here. The work, those are their work that I'm just talking here. Okay. So our objective is to maximize the power generation, right? And the power is the turbine power can be simply captured by the efficiency factor and availability, and of course the availability depends on the velocity, speed. So this power coefficient typically depend on the design of the turbine, and also depend on the operation, which is tip speed ratio. So you have, it's defined by the tip speed of the turbine compared to the velocity of the flow. So we can design the turbine to have certain shape and to maximize this power coefficient. And once it's designed, we can do the control, try to operate at the maximum speed. So we consider this two design variables, which is the chord length and the twist angle that defines the turbine design. And in control, we consider the generated load as a control variable. So if we have the sequential design problem, we maximize the power coefficient by changing those to hardware design on turbine design parameters. Then we apply control to find the optimal control trajectory that maximize the power production. Okay. Now, if we do the control co-design, we lump this two together, and we consider those three variables simultaneously. Okay. And the hard part is that we have a spatial discretization for those two physical parameters, because we want to define the shape of the blade. And for the control, we have to consider temporal discretization, because it's not just we make decision at this time, then go, right? We have to continuously make the best decision for the turbine to operate. to maximize the power production. So this leads to a high dimensional optimization problem. So the whole the key of the project is to figure out a solution that can solve this optimization problem. But the first one is to make sure that the problem is properly formulated. Then it can be solved. So in this case, we use for control trajectory, we use what we call the co-location method to parameterize the control trajectory so that we don't have to take every time instance as the decision variable. Okay. And then the problem is solved by linear, nonlinear programming. So here is the first attempt.
Question?
Yes.
The previous slide, can you explain what is meant by omega dot equals q minus u by I turbine in
Oh,
control?
this-
What are you doing there?
This is the dynamics of, this is the speed of the rotating speed.
Yeah.
And this is torque, the load, hydrodynamic load on the turbine. And that is the control action. So this is just the Newton's equation for the
I see.
for the
So
rotating.
T is IR. So U is what you apply and Q is what
What's the
the
hydrodynamic?
hydrodynamics is giving.
Yes. So here is the example that you see that we have exact same result from sequential design and CCD design. Well, you say, why is that? Well, this is because we are able, the control is able to operate at this peak speed. So you give me a design and I can operate at that speed. Okay, so control has unlimited authority. So this is a case where sequential works perfectly. You know, you give me the design and I make sure I operate at the best. So this is why, I mean, this is why the CCD and sequential will end up with same design. Okay. And the reason is that we assume control has unlimited authority. But of course, control does not have unlimited authority, right? So what if, I mean, for this size of the generator, the control has, there is authority, there's a limit on the torque of the generator that can produce. So we have a limit on the torque. Then in this case, you end up with different design. So you see, this is a CCD, and the red is CCD, and the blue is sequential. Okay. So one is with, this is because it's the CCD without constraint is the same as sequential, right? So with and without constraints, we end up with a different physical design. And this, what you see here, when we look at the trajectory, then it explains we cannot keep the optimal tip speed ratio. So we have to shift the design, and this red one is the, remember to shift it towards the higher speed so that the torque would not saturate as much. And that gives you opportunity, give us the opportunity to keep close to the tip speed ratio. Still not perfect, but compared to the others, you know, this one, the optimal tip speed ratio is here. And for the blue one, the optimal tip speed ratio is right here, but obviously you can maintain that. Another interesting thing that I think it also underscores the challenge of control co-design is What if we consider two? This is when we consider one profile of speed. Now, if we consider different profile of speed, and you do the same exercise, you end up with a different design. And of course, this is not acceptable. We cannot have a different profile for different design, right? So we have to aggregate those different operating conditions into a single design. And one way to do that is this multi-point design optimization. So for example, here we consider the flow flow distribution, probability distribution. And if you do just single-point design, then you end up with a different profile of plane. So we consider the multi-point design, we end up with this red solid line, which is different from those others. And if we look at the difference, this is when we apply the same design over the time and look at annual energy production. Obviously, this multi-point give best solution. So I want to wrap up with hopefully just some thoughts that give you something to think about the problem in this way. So we have now we do have the tool of using open loop optimum control for co-design if we can solve the problem numerically, right? But what does that give is actually this is not my last slide, but close to. But what this gives is a ceiling performance, so-called ceiling. It's the best performance we can achieve, but we cannot use this open loop optimum control because it's just give you a trajectory and it will not have feedback. If the real scenario is not exactly what you predicted, then you don't have correction mechanism. So what we want is a closed loop control. But how do you choose your closed loop control? Like in the previous example, what kind of closed loop control you choose and which one you use for feedback and which whether you use PID, proportional derivative integral control, or you use the model predict control, or you use linear quadratic optimal control, right? This is all going to impact that. So what we did in this project is we consider the physical design variables, and we also consider several different parameterized control, feedback control. One is the just linear feedback, simple. Another is a quadratic feedback, which is commonly used for wind turbine. And we also have the open loop, which is the best performance we can achieve. Now, what we learned from this is that, the open loop, the quadratic feedback achieves almost the same performance as the open loop. So which suggests that we can use this as a way of parameterize the control. So instead of making decision at every instance, the decision we're going to make is just choose the value of this K2. Okay. So so those are the performance, the final performance. As you can see that the open loop and the quadratic feedback are almost aligned to each other. Oops. So this is my last slide. I hope I convey that the control co-design does create opportunities, especially when there are interactions between dynamics of the physical system you design and control, right? But it's fundamentally a multidisciplinary problem. And like all this work that I'm control people, but all the work I've talked about working with people from hydrodynamics community and from design community. So the user CCD is not just to come up with a design, but also to discover the new interactions and to understand the new insights. So I hope that, this control after design, that paradigm can be shifted to control before build. But this does require that, the design people understand the control philosophy, and control people understand the design mindset. I find this is the most challenging part, but also the most rewarding and interesting part. So with that, thank you again for your attention, and I'll be happy to answer questions.
Thank you, Jing. Questions?
Yes.
Yes. So on the first example, you mentioned like for the control code design, you pick to do the feedback design and with different feedback gains. So is that like the gain? Your feedback gain is also part of the control design.
It is.
Design.
Yes.
So you need to optimize the gain in your control code design part.
Yeah. So in that case, the control code design is to optimize the gain together with optimize the parameter of the dead rise and the distribution, weight distribution. Yes. But the key is what parameter you decide to explore, right? And that requires some analysis and understanding of the same as in the second example. What we did at the beginning is without assume any control architecture. So do the open loop optimal control. And but that control is not implementable. But what does that do is it establishes the benchmark performance. If you put a constraint on the control architecture, you cannot do better than that in the same scenario. So later on, we find a way to parameterize the controller. So instead of find optimal trajectory, we find optimal gain. Then if that result is very close to the open loop, then you know that this control architecture does not constrain you too much. So you can get performance.
Yeah, I have a follow-up question. So based on that, I noticed that in the second example, you compare two results when you choose omega and the quadratic omega squared. But my question is like, do you think like it also will depend like if you choose either omega or the time derivative of omega, like omega dot as your
Absolutely.
Pitch example, like you pitch rate or pitch velocity or the acceleration.
Yeah, well, but that's a very good example, right? I mean, that's a very, very good question. But also that example in this second case, when we look at the quadratic feedback with speed, and we're getting close to the ceiling performance. This is the best golden standard that you can achieve. If you have one that's getting close to that, then so we also look at, for example, the linear term. If we add the derivative, if we add other things, can we get better? In theory, you can get better, but if we are already close, very close to that, you have that much little room to improve. So this is where we make a decision. This is a good structure. But like if you want to use a linear, for example, and then there is some room for improvement, then you can decide. We actually also look at linear plus quadratic, for example, and that did not improve much because there's no room for improvement. But it does improve from linear. Yeah. Good question.
So, a question about the speed profile you're using for the trajectory optimization. As I understand, these rivers are like for constant speed. So how large is the fluctuations? Like, have you ever considered just comparing with the because you also mentioned the multi-point optimization.
Multi-point, yeah.
So it looks like the mean velocity seems to have a larger influence on your design results as opposed to the speed fluctuation. I'm not
Mhm.
sure when you are doing this communication, like what's the variation of the speed over your optimization horizon, and have you ever considered like if this will have any effects on your optimization results?
Yes, I think that's a very good question, but that's a point that your control co-design, if you do the control optimization, do the co-design, the design result will depend on the profile you're considering.
Right.
So if you consider different profile, you end up with a different design, the best design, so-called, right? So it's important that you consider not just one profile, but a class of profile, and how to aggregate those into a meaningful several representative profile. That's an important problem formulation step.
Right.
So in our case, this later when we do the multi-point optimization, we do look at different speed to account for that.
So basically, if you only consider constant speed, then you don't need to optimize very long trajectories. And possibly you could optimize more speed, just more speed.
Well, yeah. So, but then that's no controls, right? If you just have the constant, everything is constant. Control is concerned about the transit, the dynamics. So if you just consider the constant, then I would say that it's still design optimization. It becomes multi-point design optimization problem, but not multi-point CCD problem.
So it's really about the transients here, like when we are involving control and early stage, we are considering this transient performance, like the performance influenced by the transients of the.
Well, transient is essential. I won't say it's the only,
Yeah,
Yeah.
I think that's why the reason we have control at the early stage.
Yes, but a control you can also have a problem where you have control limitations, for example. And when you have control limitation, but in that case, you can bring that up, you can bring that constraint into the design space and do the multi-point physical design through that. Okay. But it is when you have a transient that you cannot do that way.
Thank you.
Yeah.
Thinking that evolution, how things evolve, is fundamentally a co-design problem, where things change their shapes over a long time or whatever, based on their ability to control the system. So is this you thinking about your multi-point optimism? Does co-design, if we allow the surfaces to be smart in some way, that is interactive, could actually change it together, then does it make co-design even more powerful? Because you could now to have the means to actually get modifications to a geometry and somewhat real time. It can be a slower time scale. But if you have means to change, then co-design becomes even
think so.
more
Yeah,
powerful.
that's a
right?
good point because, in some sense, it has the element of the controls, right?
Yeah.
Because it's not the pre-scheduled
Yeah.
variation change.
Yeah.
It's response to the operation or to the variation or to the environment.
Yeah.
But the response depends on how you control it.
Yeah.
For different control, you will have different response. Then that will trigger different morphing or different adaptation of the
Then
material.
as things get
Yeah.
old or the things changes,
Yeah.
it gives some room in that space to
Absolutely.
change, then the.
Yeah.
So is biomimetic types.
Right. Yeah.
Another question I was wondering is there a thumb rule or a theory to say when co-design, you showed an example
Mhm.
and then you said, well, I don't have infinite authority. But is there a thumb rule or a theory or something to guide when co-design will make a difference and when it will not?
Well, the general rule of thumb is there are interactions between the design and control. So for example, if you have different design, it requires different control. And in the example that for the turbine without control constraints, we don't have that, right? Because you give me the design, as long as in that case, as long as you operate at the maximum tip speed ratio, the best tip speed ratio, then you get the best. And if your control can do that, then there's no interactions. So it is the interaction between the physical system and control. And if the physical design changes the controllability, and if the physical design changes the requirement for different measurements, for example, some design may make this temperature not measurable or hard to measure. Then you cannot use that as control. That information, that's interaction. So I think what I'm interested in this is every problem is different. Every problem, every project, you find new things. But there are some general rules or general tools. So how do you formulate the problem? What is the utility function that you're going to optimize? That what makes it possible to address this interaction and to explore this simultaneously?
I have one last question for me. Can you talk about how to approach problems where the cost function of the, for example, you were saying lift over drag. Now, suppose my flow is unsteady. So those things themselves are a function of time. Then how to approach that within general control framework?
Well, when we do the control design, we're always concerned about temporal response, right? There's time is always because we are concerned about the response, not just a single value, but the response, the profile. So, this time variable is always in the picture. Like in this case, what we do is we do look at not just a single point, but a time series. And this time series will be stimulated by different speed profile. For example, if you can see the speed profile with, for example, there is a ship pass by and then it causes, turbulence to the flow to the turbine, then this is one scenario of, and other is like if you have sinusoidal wave imposed on average, that's another. And if you have turbulence, then there's how we capture this turbulence as time series. If we can capture that turbulence as time series, and if there's a control can be activated to mitigate that, then that can be handled within this framework. But then the key is how do we have a model to capture that, to capture both the,
Mhm.
you know, the turbulence and also what control will impact on that turbulence, the control action that you can impact.
Is there a requirement? So now in this turbulence problem, I have blades rotating, something comes in.
Yeah,
Now the blade might stall
Yeah.
because instantaneously it stalls and produces some separation.
right.
Right. And is there a requirement that should equilibrate that? The response to this T should be faster so that the control is,
I think you're talking
should
about
be-
different time scales.
yeah, exactly.
Right? Yes, there's always different time scales. Because when you talk about control, there's like instantaneous flow disturbance.
Yeah.
And also that there's time scale of load change,
Exactly.
that's longer time. And there's also the time scale of health condition change. The biofuel build up and the
Mhm.
turbine will be different.
Mhm.
And then we need to respond to that. So yes, so this different time scale is always thing that the
And it's
control could
accounted
use.
for in the formalism.
Yes, you have to count that. But for different focus, you can have for different objective, you can have different focus when you formulate problem.
That's very neat. The formalism.
Yes. Okay.
Any other questions? One last question.
Any question from the student link or?
Yeah, I have a question. So in the
Okay.
second examples, I think one of your design variables was the chord length. My
Yes.
question is, did you have any constraints, like upper bound constraints on that parameter or not?
Oh, of course, yes. I think that we have for example, yes. Question
And-
we need to have the so we do have constraints. All physical parameters, we all have to have constraints. You have to make
And
it. Yes.
and did you check if the optimization result converge to the upper bound or not?
I don't think it converge to the upbound. No.
Okay.
We did check, but I don't think it converged to upbound.
Thank you.
Yeah, thank you
Very
for
good.
the,
Well, thank you. Thank you for
Interaction.
coming. Thank you, Professor.
all right.